Hello, in this video I'm going to show you how to solve a linear system, but it sort of follows on from my previous examples of some non-linear systems, non-linear ordinary differential equations, videos of which I did way back when. And this is a slightly different take on that. It's a more kind of traditional dynamical systems approach to solving two non-linear equations. In this case, the equations are linear, but it makes sense to start with something of a simpler nature so that we can see how um, the general pattern is for working these systems out. Now, again, they might not always be very easily solvable, and some may not be solvable at all. And there are other methods for solving these equations, which often requires some level of analysis and it's right down to graph drawing graphs of these systems to see roughly what they're doing for certain parameter values. Now, as I said, this kind of follows on from some of the non-linear stuff that I've done way back when, which then led on to some of the linear but more complex ordinary differential equations just over the last couple of so weeks that I've uploaded. Um, as I've already mentioned, we're going to attempt to solve a linear system, which is actually a heavily damped linear oscillator. And this example comes from a book on dynamical systems called Non-Linear Ordinary Differential Equations: An Introduction to Dynamical Systems. And the authors are D.W. Jordan and P. Smith. So the system that we want to solve is this system here. It's a system of two ordinary differential equations. One is dx by dt equal to y, and dy by dt is equal to minus 4x minus 5y. Now, there is a way of solving these using more traditional methods. For example, by dividing dy by dt by dx by dt and then using a substitution to solve. But in that particular case, you would get a solution x in terms of y, for example, or a solution y in terms of x. Now, we want our solutions in terms of t, which represents the time variable. And so this is a little bit more involved. So what we do to solve this system is, first of all, we get my black pen. We rewrite these two equations as x dot equals y, and I'm going to put this equation underneath, so that would be y dot equals minus 4x minus 5y. Now, because this is a system, we can write it in matrix form. So let's do that. So we've got x dot and y dot, which we put in a column matrix, and we call that big X. We're showing that that is just a vector. So x dot y dot in the column matrix is just a vector x, big X. And this is equal to, well, we have to write down another matrix as follows. So what goes in this matrix and what goes in here? Well, we've got, you'll notice, if we just write this down here, we've got x dot y dot in our matrix, and that's equal to the vector x, which is equal to, well, there is no x term there, there's only a y term. So we put 0 for the x term and y in for the y term. Here we've got minus 4x minus 5y, if you can see that. I'll just write it a little more clearly. So let's just expand these brackets a bit. Minus 5y. Now, usually what you do with matrices is you don't write the x's and y's in there. You would have a 1 there, you would have a minus 4 there, and you would have a minus 5 there, and you would take the x and y out of the main matrix. This is going to be called matrix A in a moment, and you would put the column vector xy there, okay? Because when you multiply by the rules of simple, matrix multiplication, you would have 0 times x is 0, 1 times y is y, and minus 4 times x is minus 4x, and minus 5 times y is minus 5y. So I'll just quickly run through that again. To get back to this system, we've got 0 times x, which is just 0x up here, or 0, plus 1 times y, which is just y. And of course, you just write that as being x dot equal to y. Then we move to the y dot term, and we see that's minus 4 times x, which is the minus 4x up here. And then we've got minus 5 times y, which is a minus 5y there. But we, of course, want to keep it in this matrix form. So just rewriting everything, we have 0, 1, minus 4, minus 5, x, y in the xy vector there. Okay, so what do we do to solve this equation? Well, I'm not going to go into all the theory of why you do this. You just learn that you have to do it. There is theory that backs it up, but we're just going to solve the system. Now, what we need to do is find the determinant of, and we're going to call this matrix here, we're going to call this matrix here matrix A. So we've got 0, minus 4, 1, minus 5. So we have to find the determinant of this matrix. Well, how do we do that? And also, what do we equate the determinant to? So what do we equate it to? Well, we know that I always write the determinant this way round. A lot of mathematicians will write A minus lambda I for the determinant of a matrix, but I don't like that way, because quite often it means you have negative lambdas which eventually become positive. But for me, I'm absolutely appalling with negative signs, and if I can help it, I like to keep everything positive where necessary. So what I do is I write the determinant as being lambda I minus A. So what's that equal to? Well, let me do a little bit of rough work on the side. Lambda I is lambda times the identity matrix minus this matrix A here, 0, minus 4, 1 and minus 5. Right? So if you multiply lambda by everything in that bracket, you've got lambda with 2 zeros there and a lambda there minus 0, 1, minus 4, minus 5. And if you just simplify this, you get in the top, you get lambda minus 0, which is just lambda. Here you've got 0 minus 1. So we've got a minus 1 here. Now here we've got 0 minus a minus 4. So that becomes plus 4 there. And here we have lambda minus a minus 5. So it becomes lambda plus 5 there. Now that is the matrix A. I'll just write that on there for now, but I'm going to rub it out because we're going to rewrite it on this line above. So we've got lambda minus 1, make that look more like a lambda, and 4 and lambda plus 5. Okay? Well, actually, we haven't worked out the determinant yet. The determinant is, in fact, what we should have are modulus signs, effectively, for the determinant. So that is the determinant of that matrix. And of course, when we work that out, we find that lambda I minus A is equal to lambda times lambda plus 5 minus a minus 1 times 4. Okay? So, let me just erase this. So this simplifies to give lambda squared plus 5 lambda. Minus times a minus is a plus, so it's plus 1 times 4 is just 4. And a determinant always has to be equal to 0. Your determinant in these particular cases, in this theory, always has to be equal to 0 for this to work. So always remember that. Now this can be factorised on the left hand side. So we get lambda there and lambda there, and we want two numbers which when multiplied together give 4 and when added give 5. And those numbers are 1 and 4 because 1's 4 is 4 and 1 plus 4 is this 5 here. So 1 times 4 is 4 and 1 plus 4 is this 5 here. So we'll just erase those little underlines, and of course they're both positive because these are both positive here. So we see that lambda plus 1 is equal to 0, or lambda, in fact I'm going to write my plus 4 up there. Lambda plus 4 is equal to 0, or lambda plus 1 is equal to 0. This implies that lambda is equal to minus 4, or lambda is equal to minus 1. And I've written the lambda plus 4 up there ahead of writing down the lambda plus 1 because we get a minus 4 which is less than minus 1, and I always like to work in kind of chronological linear format, and then I make fewer mistakes. So minus 4 is it's smaller than minus 1, so we start there. It's just my little it's a little idiosyncrasy of mine. So we know that lambda is -4 and lambda is -1. Now we have to, we're not finished yet, because if I just erase this, we have to now find the eigenvectors. So these values for lambda are the eigenvalues. So these are the eigenvalues. And these, what we now need to find are the eigenvectors, as I've said. So let's just write that down in full. Eigenvectors. So how do we do this? How do we find the eigenvectors? Well, we know that A is equal to, in fact, we're using this matrix here. We form this back into a matrix, so we call it matrix B. Let me just, there we are. So we write down matrix B. And so we've got lambda -1 and 4 lambda plus 5. Right, okay. Now, I'm going to put the X and the Y in there as well, because when it's a matrix, there's got to be X and Y values in it. Yeah? So, when lambda is equal to -4, we have, I'm going to ignore writing the B bit down. We have -4 and -1 stays as -1, and the 4 stays as it is, and we've got -4 plus 5. I'll write it down for you. So that's on its own, and that is equal to, in fact, actually I should have the X and Y in there, and that's equal to -4 -1 and 4 and 1. Let's just put more of a gap in there. -4 -1, 4 and 1 times X and Y. Now, when you multiply everything out there by X and Y, we get 2 identical equations. So what we get is -4x minus y minus 1 times. So we've got -4 times x minus 1 times y. And also on the bottom we've got 4x plus y. These are exactly the same, except that that has got minus signs in front of it. Well, if you cancel the minus signs, then what you've got is a single equation, 4x plus y. So you can just take that one equation. Now, the eigenvectors, I found this really difficult to understand when I was at university, because no lecturer, no other student, absolutely no one else ever explained that this is what we were doing. And if they'd told me and gone through it literally step by step, that's what I needed, the baby building blocks of how to understand mathematics, and if they'd done that, I would have had no trouble. So hopefully my explaining to you how to do this will help you. Now, you usually, in fact, I think in nearly all cases, if not all cases, you come out with a single equation like this. And so an eigenvector has to be equal to 0 when you put certain parameter values in for x and y. So what we've got is, to make this equal to 0, and that's why these minus signs disappear. There you are. So when that matrix is equal to 0, the minus signs there disappear, and you've just got that same equation. So to make that equation 0, we need to choose any values we want for x and y, providing that they make this equation equal to 0. But the simplest ones would be to choose x equals 1 and y equals -4. Why? Well, because 4 times 1 plus a -4 is just 4 minus 4, which is 0. So do you see why I've chosen x to be 1 and y to be -4? This is just one of an infinite number of eigenvectors. So we've got 1 and -4. And because there are an infinite number of eigenvectors, what we do is we write v1 is equal to some constant times that, because you can have any multiple of this eigenvector that you want, or that suffices for the system that you're modelling. Right, so we've got one eigenvector. Now, what about when lambda is equal to -1? So, when lambda is equal to -1, we've got our matrix. We'll just write it down here. So we've got -1, -1. And here we've got, well, the 4 stays as it is. And we've got -1 plus 5. -1 plus 5 in brackets. Let's make that look like a more convincing curly bracket. And this is your x and this is your y. Okay, so let's go to the other side of the board. Right, okay, let's just draw this green line down here like that. Right, okay, so this simplifies to -1, -1, 4 and 4, and there's your x and y. And of course you can see that this is just a multiple of that when that all of that is equal to 0. So we've got -1x -1y and 4x plus 4y equal to 0, equal to 0. So I'm writing it out here, whereas I didn't write it out for you before. So we've got these two equations which are clearly multiples of each other. So we've got x plus y equals 0. So what is an eigenvector for that system? Well, clearly, if you substitute 1 for x and -1 for y, you get 0 on the left-hand side. So choose x equals -1. Sorry, we'll have x is equal. You could actually choose x to be minus 1, but we'll choose it to be 1 and y equal to minus 1. And we'll check that it works. So we've got 1 plus a minus 1. So that's the left-hand side. And that is equal to 1 minus 1, which is 0. So another eigenvector is v2 equal to b times, in bracket, 1 and minus 1. Okay, so we've got two eigenvectors now, and we've actually got the two eigenvalues as well. So we've got lambda equals minus 4, which corresponds to this eigenvector, and we've got an eigenvalue of lambda equal to minus 1, which corresponds to this eigenvector. Now, take it from me, it's in all the books, and you can verify this for yourselves if you do some research on these, in these areas. But two solutions are x equal to a times v1 e to the lambda 1 t plus b v2 e to the lambda 2 t. And in fact, yeah, that would be the vector x. So in other words, what we've got is x and y in our column vector, not x dot y dot this time, just x and y, is equal to a v1 e to the lambda t, e lambda 1 t plus b v2 e to the lambda 2 t. Okay, right, so what we can write down now, and we're getting very close to the final solution, we can write down and substitute all of this information into this equation here. So we've got a times, well, our first eigenvector was 1 and minus 4, or a times, in the column part of the matrices, 1 and minus 4. So 1 minus 4 e to the power, well, we know that lambda is minus 4. So it's minus 4t plus b times this column vector here, which is 1 and minus 1, times e to the power of lambda equals minus 1 there. And that is your solution. Now I'll just explain a little bit more detail what this means. It means that x is equal to some constant times e to the minus 4t plus b e to the minus t, and y is equal to minus 4a e to the minus 4t, right, plus b, in fact actually it's a minus, isn't it? B times minus 1 is minus b e to the minus t. So we have two solutions, one for x in terms of t and one for y. And I'll just quickly draw what the phase portrait or the graph of those two solutions look like. I'm not going to explain it because really that's a whole load more theory, and I don't want to be prolonging the video unnecessarily. But basically what you have is, if we draw a circle like this with our y axis and our x axis, there's another line that goes through here, and I'm not going to state what that line is and where it comes from, but basically I think you have another line through there as well, somewhere up here. But basically what's happening is the solutions are just 1 minute, I'm making a pig's ear of that, do pardon my French. So let's just fill that in. Right, so what we actually have is a system that does this, with the arrows tending in towards the centre. And similarly, on this side, we have the arrows approaching the centre. It looks a bit like a stable saddle point, but it isn't. It's just a phase portrait of this system and indeed the initial system of ordinary differential equations. So I hope that that's been okay, and that you feel that that has explained something that perhaps you weren't sure about before or didn't know, and that you will come back for more videos as I gradually progress with putting more videos up. So until the next time, I'll bid you farewell for now, but all that remains for me to say is see you later. Okay, cheerio, bye.